Hi, welcome back to Statistics. I wanted to record for you a video from section 10.3 because the video in Canvas has more information than what you really need for section 10.3. As we go through section 10.3, you'll need your notes for 10.3, your calculator, and table 7. Let's begin. So we've been talking about a hypothesis test. And the whole ideal of a hypothesis test is to see whether or not our educated guess is true. In 10.1, we talked about our null and our alternative hypotheses. We also talked about a type 1 and a type 2 error. Today, we're going to look at actually carrying out that hypothesis test. So imagine that you have a college algebra instructor that's announced that 2,000 students took the midterm and the population mean was 85. You poll a random sample of 50 students and you find that the mean is 83. Now make sure that your notes have 83 here. So suppose you do some calculations and the probability of finding a sample with a mean of 83 is 0.25. So even though our sample mean is a little bit less than the instructor's claim, it's not too far off. We don't have a really strong probability to say that it's too far off because 25% probability, that's kind of likely to happen. I know it's not quite that close to 1, but this is not an unusually low probability. So remember that unusually low is that typically a rule of thumb of 0.05 or smaller. So this is not an unusually low probability. This is an acceptable probability. Now, on the other hand, let's suppose that we take a random sample of 50 students and the mean is actually 60 for that random sample. Now, the chance that a sample mean is going to be 60 when our population mean is 85 is very small. It's 0.02. So this tells us this is unusual. That's less than that 0.05 rule of thumb. So two things could happen. Either 85 is the correct population mean, and we just took a really unusual sample, which could happen, or the population mean is really less than 85. Now this second possibility is the more likely of the two. We would probably conclude that the probability of a sample mean of 60 is too low, that 0.02, that's a very small probability. So our instructor's mean is likely wrong. Now, by the way, be sure that your notes have an 85 here and not a 0. So the question is, where's the cutoff? How do we know how small we can accept that probability or how large we can accept that probability? The process of hypothesis testing helps us turn our gut feelings into numbers that we can analyze. In hypothesis testing, the main idea is to compare the probability of getting a certain sample mean to a level of significance, which this is the smallest probability we're willing to accept by chance. Now remember, from 10.1, alpha is our level of significance. On the top of the next page, we have some more blanks. If the probability of obtaining a sample mean by chance is less than the level of significance, we take that as evidence that the null hypothesis is wrong. In other words, what's going to happen is we are going to reject the null hypothesis. Now, there are two approaches with hypothesis testing. The first approach is called the classical approach. And this is the approach that we are going to focus on, is the classical approach. We compare our t-score to a test statistic. That's our t-score is that test statistic. And we compare it to a certain critical value. That critical value comes from Table 7. The p-value approach looks at the probability of obtaining the sample mean, kind of like we talked about at the start of this section. It compares the p-value to the level of significance. If our p-value is less than alpha, then we reject H naught. Now, you're going to see some problems where you're on the sample final and also on the final exam where you're asked to compare p to alpha. So if p is less than alpha, you'll be given that p-value. Then you reject your H naught, your null hypothesis. Now, unless you're using a spreadsheet or other type of computer program, or you're using a TI 8384 graphing calculator or other type of graphing calculator, the p-value is difficult to work with by hand. That's why we are going to focus on that classical approach, and it's a great introduction to our hypothesis testing. So we are only going to work with the classical method. So you can draw a line where it says we will work with problems using both methods. Now, even though we are going to focus on the classical approach, keep in mind that in the real world, a lot of times the p-values are what are used. Our steps for our hypothesis testing are as follows. First, we find an SRS, a simple random sample. Or we use a randomized experiment. We need to check to be sure that our sample has no outliers. And we also need to have either a normal population or that large sample size. Remember, 30 is our magic number, and make sure that that inequality is correct in your notes. So our sample size has to be 30 or more. And last, our values are independent of each other. This means they do not affect each other. This brings us to the top of page 3. Here are our steps for carrying out a hypothesis test using the classical approach. And again, we'll be focusing just on that classical approach. First, find your null and alternative hypotheses. Second, select a level of significance. Now, this alpha will be given to you in the problem. Third, we're going to compute our test statistic, and you'll see the formula for that test statistic. We use our t-table. This is table 7. we find that t value based, or critical value, based on our alpha. Now, I like to draw my curve because it gives me a picture, and I'm a very visual person, so that picture helps me see what's happening. Then I compare my test statistic to the critical value. If it falls in the shaded region is going to be the tails. Now, if it's a right-tailed or left-tailed, we'll just have one tail. If it's two-tailed, obviously we'll have two. If the test statistic is in the shaded region, we reject the null hypothesis. And if it is not in the shaded region, we do not reject the null hypothesis. That brings us to example 1. So I'll give you a little bit to read through the problem. Now notice here a couple of things. We have 43 presidents that we're going to look at their heights. That's our sample size. The 70.78 is our sample mean. And the 2.77 is our sample standard deviation. Also notice that we have our level of significance here. And we want to know, are U.S. presidents taller than the average American male? So our first step, you'll see in your notes, is to write the hypotheses. Our null hypothesis will be mu equals, and here the mean height of American males is 69.5. Our alternative hypothesis, we bring down that mu, and we want to know if presidents are taller than average, so that would be a greater than. And our units here are inches. Step 2, we find our alpha. Our level of significance is 0.05 here. Alpha should always be given to you in the problem. If it's given to you as a percent, change that percent to a decimal. Step 3, if you write large, you may need to write a little bit smaller in your notes for step 3, because there's a good bit of information we have to put in this place. So step 3, we're going to find our test statistic first. So our test statistic, our formula is this. Now, most of the time, you're going to see me write that denominator rather than as a fraction with one on top of the other. I'll write it side by side with still my fraction bar because that saves me room. Our X bar, the mean heights of U.S. presidents were 70.78. Mu naught comes from the null hypothesis. And so mu naught here is 69.5. Our standard deviation is 2.77 divided by, and n here is 43. Type this into your calculator. Now, when you type this into your calculator, you need to be sure that you put the numerator in parentheses as well as that whole denominator in parentheses. Pause your video, type this into your calculator, and once you have your number, resume the video. Once you type this into your calculator, you should get 3.030. This particular test is a right-tailed test. I know it's a right-tailed test because of the greater than in my null alternative hypothesis. I'm going to go to table 7 here in just a second. Now with table 7, I need to know two things. I need to know what row and what column. So our row is our degrees of freedom. So n minus 1. Here, 43 minus 1 is 42. And again, that tells me the row on table 7 to look at. Now the column comes from the area in the tail. I'm going to leave a space, and I'm going to go ahead and sketch a picture. This is a right-tailed test, so the area in that tail is that level of significance. That 0.05 comes from our alpha. And this tells us which column to look at on our table. Now the critical value I'm going to abbreviate as CV. So let's turn to table 7 and look at the row and the column to get our critical value. We don't have the number 42 on our table, so we choose the number closest to it, and that would be 40. Our alpha here is 0.05, that's our column. And you'll notice here that our critical value will be 1.684. I can label this point down here as 1.684 on my number line. Now the 0.05 is my shaded region. I'm going to go ahead and shade it. I'll shade it using my green. And what I want to know is my test statistic in the shaded region? Well, my test statistic was 3.030. 3.030 would be somewhere over here. And so is the test statistic in the shaded region? The answer is yes. This tells me then to reject the null hypothesis. Now we always need to put our concluding statement in terms of the actual problem. So we would say something like this: there is enough evidence or sufficient evidence to conclude and I want to think about this problem. We were wondering if U.S. presidents were taller than the average male. And so the answer is yes. So to conclude that the mean height of U.S. presidents is greater than 69.5 inches. In other words, U.S. presidents are taller than the average American male. Now, at any point in the video, if I move on and you've not finished copying the notes, pause the video, finish copying what you need to, and then restart the video. On the top of page 4, we have our next few blanks to fill in. Our hypothesis testing requires a normally distributed population or that large sample size. Remember, 30 is our magic number. If we have outliers in our sample, then we should not use hypothesis testing. Now, if our sample size is small, doesn't meet that 30 or more, we use our box plots and our normal probability plots, just like we did with our confidence intervals, or just like we talked about with our confidence intervals. Our next exercise talks about the mean waiting time for a drive-through. Go ahead and read through this one. Notice we have our sample size is 10. Now this does not meet that magic number, so we'll have to look at our normal probability plot and our box plot. The 0.1, that's our level of significance, that's our alpha. And this particular problem, we have the words decrease. And so this tells me that I'm going to have a left-held test, because decrease is to the left of. Here's our data. We'll come back to the data here in just a moment. Now we have a small sample size. We have only 10. So the manager uses a normal probability plot and a box plot. And he does verify that we don't have outliers and we do have a normally distributed population. So that brings us to our steps. Now the first thing I want to do is I want to find my mean and my standard deviation. Remember that we're not going to be using a graphing calculator this semester, but I did show you in class how to use your calculator to find the mean and the standard deviation. First, go to Second and Stat. Scroll over to Clear Data. Always clear out your data first. If you don't clear out your data, you'll mess up your answer. Then go to Second and Stat. And we have only one variable here. We have the wait time. And your data you enter under the data key. You'll have your X1, and you'll type in that X1 from your table on page 4. Then that FRQ, remember to just scroll through. Then X2, scroll down through the FRQ, it should be 1. Then type in your X3 and so on. Once you have your data typed in, you'll press the Stat Var key. Pause the video, type in your data, and press the Stat Var key. You should have that X bar is 78 and S is 15.21. Now our units here, these are wait times in the drive-thru, and so our units are in seconds. Our first step is to write our hypotheses. So our null hypothesis is mu equals, and the average wait time is 84.3 seconds. Our null hypothesis is mu equals, and we have a decrease, so it's not equals. The alternative will always not be equal. It'll be a less than, a greater than, or a not equal to. This one has decrease, so it'll be 84.3 seconds. And I'm going to scroll over to Notability once again. Just to review, we found our X bar was 78 and our S was 15.21, and that comes from the calculator. Our step 1 is our hypotheses. So our null we just said was mu equals 84.3 seconds. And our alternative was a decrease, so that's a less than. Step 2 is our alpha. The problem tells us that alpha is 0.1. Step 3. We need to find our test statistic. Now again, if you write small to get this all in your notes, you may need to write, if you write large, you may need to write a little bit smaller. Here's our formula for that test statistic. We found that X bar was 78. Remember, mu naught comes from the null hypothesis. And here we have 84.3. Our standard deviation was 15.21. And our N here is 10. When you type this into your calculator, make sure you put parentheses around the numerator and around the denominator. Pause the video and type this into your calculator. You should have gotten negative 1.310 for your test statistic. Typically, you're going to see about 3 decimal places with those test statistics. Now, to find my critical value, I'll need to go to Table 7. And remember, critical value I will abbreviate as CV. I need to know my rho. That comes from my degrees of freedom. Your degrees of freedom are your sample size minus 1, or 10 minus 1 here, which is 9. Now once again, I'm going to go ahead and sketch a picture. I'm skipping a space for a reason. This particular problem talked about decrease, so this would be the left side, or the left tail. And I'm going to go ahead and shade that left tail in green. Now the area of this left tail is that alpha, and so that area is 0.1. Our alpha here is 0.1. The 9 tells me which row on table 7, and the 0.1 tells me which column. So here's my table. I'm going to the row that has the 9 and the column with the 0.1. And notice here I get 1.383. Zero is in the middle of my number line with my t-values. So rather than being a positive, since I'm to the left, my value would be a negative 1.383. And so my t alpha over 2 is negative 1.383. Step 4. I want to know, is my test statistic in the shaded region? Well, if I look back up at my test statistic was negative 3.10. Negative 3.10 is about right in here on my number line. And so no, the test statistic is not in the shaded region, and so we do not reject H0. We always need to write our conclusion in terms of this particular problem. So we would say something like this. Because we do not reject H0, there is not enough evidence to conclude that the mean wait time is less than 84.3 seconds. In other words, this new drive-through system that the manager devised, it did not decrease the wait times significantly. We've looked at a left-tailed, we've looked at a right-tailed. Now let's look at a two-tailed test. And that's our next example. Go ahead and read through this example. So the fun size of a Snickers bar is supposed to weigh 20 grams. The machine, because the penalty is severe, the manufacturer calibrates the machine to weigh a little bit more than that, 20.1 grams. So that's kind of the mean that we're trying to get here. We have a random sample of 11 candy bars. So 11 is our N. We have our alpha of 0.01. And we want to know, should the machine be shut down and calibrated? So what happens here? If the machine has the Snickers bars weighing too much, the company is going to lose money. So that's that right side. If the machine has the bars weighing too little, the company is going to have to pay a penalty. So that's that left side. So because we have the left and the right, too much, too little, this gives us a two-tailed test. Now, if you look at this normal probability plot, if we were to go through and find the values, this one is close to normal, about as close as we're going to get. We do have to check this here because we only have 11 in our sample. We don't have that magic number of 30. The box plot shows us that there are no outliers. Now you'll notice here you have your table 1, which has the values, the weights of those Snickers bars. We need to know the mean and the standard deviation of those Snickers bars. Now to find the mean and the standard deviation, you use your calculators. Remember on your calculator, the first thing you do is go to Second, Stat, clear your data out first. If you don't clear your data out, it can mess up your values, and hit Enter. Then go to Second and Stat. We have one variable here. The only variable we have is the weight of the Snickers bars. And third, remember to enter your data under Data. Just scroll down anytime you see that FRQ, it should be 1, and leave it as 1. Once you have your data entered, you press the Stat Var key. Go ahead and enter your data and find X bar and S. Pause the video while you do so. You should have gotten that X bar is 20.301, and here we're looking at grams for our units, and S is 0.64 grams. For step 1, we write our null and our alternative hypotheses. So our null hypothesis here, mu should be 20.1 grams. The alternative hypothesis, we don't want too much, we don't want too little, so that's a not equal to. Step 2, the problem tells us what alpha is 0.01. Now notice our alpha is small here because there are some quite large consequences if we don't carry out our hypothesis test correctly, or if we make that type 1 error. Step 3, we find our test statistic and as well as our critical value. If you write large, you might want to write a little bit smaller so you can get everything in that space. The formula for our test statistic is this. X bar here was 20.301. Mu naught, remember, comes from our null hypothesis. So here, that should be 20.1. Our standard deviation was 0.64, and N here is 11. When you type this into your calculator, make sure to put parentheses around the top and around the bottom. Pause the video while you type this into your calculator. you should have gotten 1.042. We need to find our critical value, so we go to Table 7 to find that critical value. Our degrees of freedom are sample size minus 1. So here, 11 minus 1, or 10. Now, as I start to draw my picture this time, I have the not equal to, which is a two-tailed test. So I shade both tails. Now, alpha is the area in both tails. I want to find the area in one tail, so I divide alpha by 2. Our curve is symmetric, so our tails are the same. Our alpha here was 0.01. Divided by 2 is 0.005. So each tail has an area of 0.005. And remember, 0 is in the middle of my number line. The degrees of freedom tell us our row, and the 0.005 tells us our column. Turn to Table 7 and find your T alpha over 2. So the row that we look at is 10. We have 0.005 for our column. And notice here I get 3.169. This value on the right then is 3.169. That's the area to the right for that Table 7. And over here, I'd have the opposite value of negative 3.169. And so our two critical values here are plus and minus 3.169. A two-tailed test will always have two critical values. Step 4. Is our test statistic in the shaded region? My test statistic was 1.042. 1.042 is somewhere right in here. So our answer here is no, and we do not reject H naught. In the context of this problem, we would say something like this. There is not enough evidence or sufficient evidence to conclude that the mean weight is different from 20.1 grams. In other words, the quality control engineer does not have to shut down and recalibrate the machines. page 7, we start talking about the p-value. You can draw a line through those steps at the top of page 7. I do want to talk about the comparison of alpha and the p-value that's in the middle of that page. With the p-value approach, the only thing I expect you to know is this. If our p-value is less than alpha, then reject the null hypothesis. So on your sample final and on your final exam, you're going to see something like this. Suppose the p-value is, let's just say, 0.023. And alpha, our level of significance, is, let's just say, 0.03. What conclusion should we draw? In other words, do I reject H naught or not? So my question is my p-value less than alpha? And the answer is yes. If your answer is yes, then you reject H naught. Let's look at another. Suppose the p-value is 0.05 and alpha is 0.025. What conclusion should we make? The question we ask is our p-value less than alpha? Our answer here is no, and so we do not reject H naught. On the bottom of page 7, you have some more bullet points there. You can draw a line through those. On the top of page 8, I'm not worried about that example 1B. You can put a line through all of that page. You can draw a line through all of page 9, all of page 10, and that brings us to page 11. So what is hypothesis testing all about? We have to think about statistical significance. That's when we reject H naught. So statistical significance is rejecting H naught versus practical significance. Sometimes we can reject H naught, but it doesn't have any application in the real world. For instance, it's likely sometimes to get a small p-value with unlikely things in large samples. For example, studies have been done that show that wearing a lab coat causes people to think more carefully, that spanking causes cancer, or that autism is caused by highways. None of these have practical significance. They did have statistical significance, where the null hypothesis was rejected, but it doesn't really have practical applications for us. From a website, wmbriggs.com, epidemiology, that's the study of diseases, I believe, is nothing if not a productive field. All that is needed for success is a database. The larger the database, the better. A disease, and some minor facility with statistical software. And you can make statistics say whatever you want. Daryl Huff wrote the book, How to Lie with Statistics. It's actually a very interesting book, and I have read that book. If you torture the data long enough, it will confess to anything. Now, what it comes down to is if something violates your common sense, don't change your mind just because a hypothesis tells you to reject the null hypothesis. Use common sense as you're using statistics. The good news is this is our last lesson for this semester. If you have questions, let me know.